right, in this video we're going to start to look at section 3.6, where we're looking at second order differential equations. And in particular, we're looking at second order differential equations that look like this. A copies of the second derivative y double prime plus b copies of y prime plus c copies of y, where a, b, and c are just real numbers. So, a couple of vocabulary words to qualify the type of second order differential equation we're looking at. First of all, it's second order. Now, all that means is that a can't be zero. We've got to have some second derivatives here and nothing higher than that. So I don't have any third or fourth derivatives, but I do in fact have some second derivatives. So b and c are allowed to be zero, but a is not. Second, this is linear. Now, linear just means that if I were to solve for y double prime, I would be able to write it as some function. I'm just going to write b of t times y prime plus c of t times y plus d of t. So I could express the second derivative in terms of some y primes, some y's, and some functions of t, and I'm also allowed to have functions of t as my coefficients in front of y prime and in front of y. Now obviously here, if I were to solve for y double prime, that would mean that y double prime was negative b over a y prime minus c over a y. So this is somewhat specific because I can see I don't have any functions of t. So it's linear because it does satisfy this, but it's also homogeneous. Now, homogeneous just means that d of t is zero. So that means that I can express the second derivative as some y primes and some y's. Still allowed to have functions of t as my coefficient functions. Okay. This one, we happen to have constant functions of t as our coefficient functions. So this is also constant coefficient. So that just says these guys are going to be constant functions of t. There are no t's. And if I put all of this together, of course, that makes it autonomous. Now at this point, it's redundant to say that this is autonomous, because if it's both homogeneous, so that I don't have any of these, and constant coefficients, so that's just a c and that's just a b, then it's going to be autonomous. That just means I can write without ever having to write the symbol t, so that the only way that t shows up is with the understanding that y, and then of course y prime and y double prime, are unknown functions of t that I'm trying to solve for. Okay. All right, autonomous is a word in and of itself though, because it's possible for something to be autonomous but not homogeneous. For example, if I did have a constant function here, then it wouldn't be homogeneous, but it would still be autonomous. So these vocabulary words are distinct from each other, but once I have the combination of these two, I automatically have that it's autonomous. Okay, so we're going to be taking a look at solving these things, and I want to remind us that the main application that we saw of these was when we had a harmonic oscillator, and that was of course our infamous mass attached to a spring, whoops, there's a spring there, with of course our friend Moose the massless mouse going for a ride on this harmonic oscillator as it goes back and forth. When we had that, we would let y be our signed distance from the rest position, and the equation that we got there, we would have m was equal to the mass, which of course has to be bigger than zero. You can't have a negative mass. And while we do have Moose the massless mouse, we are not studying a massless mass attached to a spring. We are studying a full mass attached to a spring. Okay. So the total force acting on things we got from Newton's law was just the mass times the acceleration, which would be the second derivative. Okay. But we also had that we would have B, which is our damping force, or damping coefficient, which was also a positive constant, and we would have K, which was our spring constant, which was also a positive constant. Okay, and the total force, we said, was equal to the restoring force, not the restoring force, the damping force plus the restoring force of the spring. So the damping force, that was the combination of friction and air resistance. We said that that was going to be proportional to the velocity, but it was going to act in the opposite direction. Okay? So that if the mass was trying to move in this way, the damping forces are pushing it back. So if B is a positive number, we take a negative copy of B and multiply it by the velocity. Then this was our restoring force. So this was our damping force. This, we said, was the total force. And this is what we're going to call our restoring force. And that's just the spring wanting to get back to rest position. So that's proportional to the assigned distance that it is from its rest position, and it acts in the opposite direction. So if rest position is here, and I'm over here on the positive side of it, the restoring force is wanting to act in the negative direction to bring me back to that rest position. Okay. So if I were to add everything over to one side, I would get something that looked like this. So I've just got M, B, and K as my coefficients rather than A, B, and C. Okay. So if we have a differential equation like this, where all of these coefficients are positive, or I guess they could be zero, because we could have an undamped harmonic oscillator, so B could be zero. But if I don't have any negative values for A, B, and C, then I know that my second order differential equation is going to correspond to some sort of a harmonic oscillator. Actually, I guess if it's a harmonic oscillator, C would have to be non-zero, and it would have to be strictly positive. So if I have positive coefficients, or at least non-zero for B, I could have a non-damped harmonic oscillator, then it corresponds to this situation. In this section, we're studying generic ones. So the rule is when we're modeling, we always set our parameters equal to positive values, and if we want to have a negative value, we just put a negative sign in there. Okay. So if I'm trying to model a real world situation, I will use the rule that all of my parameters are positive. But here, I'm not really using these, well, I guess they are parameters, but I wasn't modeling a situation, I'm just trying to describe a generic differential equation. And so A, B, and C are allowed to be negative in studying the generic case. So some of the problems that we do will correspond to harmonic oscillators if A and C are positive and B is non-negative. If we have any negative numbers in there, then it's still one of these second order differential equations. It just won't correspond to the harmonic oscillator. Okay, so what I want to do is compare a differential equation that's second order like this to its corresponding system. So I'm going to just divide my board here into two pieces, and we said we could create a corresponding system because we could work with Y and V, where what we do is we say that Y prime, if we're creating a system where we've got the derivative vector here, so it should have been Y prime, V prime. Y prime is just V. Okay. So we say V is going to be the first derivative of Y. And of course, the reason we call it V is because we're thinking in terms of the harmonic oscillator, where Y was a position function, and so its derivative is velocity. Okay. And then V prime, we should be able to express in terms of Y and V. Earlier, I had solved this for Y double prime. and we had gotten that it was negative b, sorry, let me first of all divide through by a. So I get y double prime plus b over a y prime plus c over a times y is equal to 0. It's not necessary to do that first. I'm just trying to match the notation in the book, because then they call b over a p and c over a q. And so when I solve for y double prime, then I'm just subtracting these guys over. So I'm going to get negative q times y minus p times y prime, which means v prime is negative q times y minus p times v, because v, of course, is the name that we've given to y prime. So we get a system that looks like this, but notice that that's equivalent to a linear system where I'm simply calculating my derivative by multiplying by a 2 by 2 matrix. If y prime is just v, that's 0 copies of y and 1 copy of v. And if v prime is negative q copies of y minus p copies of v, I get a matrix that looks like this. Okay. So, in the previous sections, we studied all linear systems where I could have a generic matrix here. Linear systems that correspond to one of these second-order differential equations will always lead to a matrix where I've got 0 here, 1 here, and then arbitrary numbers here. Okay. Now these are arbitrary because Q, remember we said, was just C over A, and C and A were arbitrary, and P was B over A, and B and A were arbitrary. If I have a harmonic oscillator where A, B, and C are positive, then these guys would be negative numbers. If it's an undamped harmonic oscillator, B would be 0 and P would be 0. Okay. But if I'm corresponding to just a generic linear system like this, I'm going to get a matrix like this. Some of these will correspond to harmonic oscillators, and some of them won't. Okay. So what I want to do is just compare the techniques that we have for solving these things, because we spent a lot of time on linear systems. And I'm hoping that the knowledge that we got for these linear systems is going to translate back to some knowledge that we have for these second-order differential equations. So that's where we're going, and that's where we'll pick up in the next video.